Imagine a universe where a colossal shift transforms the night sky into a blazing beacon, where Jupiter, the giant gas world, ignites into a second sun, bathing our solar system in unprecedented light and heat. The silence of space would shatter as the sky is painted with an ominous, blazing glow, casting long shadows and redefining the very fabric of planetary life. With that fiery emergence, worlds would tremble, oceans boil, climates spiral into chaos, and the boundaries of night and day blur into an eternal twilight. What if this enormous planet, once a distant gas giant, suddenly became the star anchoring our celestial neighborhood? How would our Earth endure? And what secrets does this hypothetical reveal about the delicate balance of cosmic forces? It's a story of scale, power, and transformation, one that makes us ask if the universe's greatest wonders could someday become its greatest threats. The current state of Jupiter and its composition. Jupiter dominates the solar system with its colossal presence, a swirling sphere of gas that ignites the imagination. Its atmosphere is a captivating tapestry of swirling clouds, towering storms, and bands of color that stretch across the planet's face. Predominantly composed of hydrogen, about 90%, and helium, around 10%. Its gaseous makeup resembles a miniature star's primordial ingredients. Beneath this luminous veil of clouds lie layers of complex molecular compounds, including ammonia, methane, and water vapor, all churning in a ceaseless dance driven by intense heat and gravity. These clouds form striking belts and zones that shift with the planet's rotation, creating a constantly evolving display of light and shadow, a cosmic ballet of energy. The core of Jupiter remains one of the most profound mysteries in planetary science. It's believed to harbor a dense, metallic hydrogen layer, possibly containing a solid or semi-solid core roughly the size of Earth, but many times more massive. Temperatures increase dramatically as one moves inward, reaching tens of thousands of degrees Celsius within the deeper layers, hot enough to ignite thermonuclear reactions if conditions were just slightly different. The core's exact composition is still debated. Some models suggest a rocky or icy center surrounded by layers of metallic hydrogen that generate powerful magnetic fields, tens of thousands of times stronger than Earth's. This magnetic field traps energetic particles, creating the spectacular auroras at Jupiter's poles, which glow with an intensity that outshines most celestial phenomena in the night sky. Jupiter's immense size. Its diameter exceeds 139.0 kilometers, and mass account for about 1/1000 th of the Sun's, but more than twice all of the other planets combined. Its vast gravitational pull influences not only its numerous moons, but also the asteroid belt and the overall dynamics of the solar system. The planet is constantly radiating more heat than it receives from the Sun, a remnant vitality from its formation that fuels convective currents within and causes turbulent storms that rage for centuries. The Great Red Spot, a hurricane-like storm 3 times larger than Earth, has persisted for at least 350 years, embodying the planet's restless energy and turbulent atmosphere. If Jupiter were to somehow shift into the role of a second sun, the implications would be staggering. Its composition, rich in hydrogen and helium, suggests that its potential to ignite nuclear fusion hinges on achieving a critical mass and core temperature. Though technically a failed star in its current state, it teeters on the edge of stellar self-sustenance. If it somehow crossed that threshold, the entire fabric of the solar system could be reshaped, light and heat pouring into the void, new zones of illumination, altered planetary orbits, and perhaps an entirely different cosmic harmony. As we contemplate Jupiter's awe-inspiring power, one wonders, what does it truly mean for such a planet to hold the potential for becoming a star? Would the universe then question itself anew? What is the destiny of worlds caught between the categories of celestial giants? The concept of a second sun and stellar formation. If Jupiter somehow transformed into a second sun, the implications stretch across cosmic scales, igniting questions that border on the divine. At their core, stars form through the gravitational collapse of dense clouds of gas and dust within galaxies, typically hydrogen, triggering nuclear fusion once the core temperature rises to millions of degrees. This process converts gravitational energy into thermal energy, igniting sustained fusion reactions that produce immense light and heat. Such events are rare and complex, requiring vast amounts of material and the right conditions for gravity to overcome internal pressures. Jupiter, a gas giant primarily composed of hydrogen and helium, already contains a significant amount of these elements, but it's far from the mass threshold necessary for fusion. To be classified as a star, Jupiter would need to be roughly 80 times more massive, a threshold known as the hydrogen burning limit, stretching from a giant planet into a proper stellar object. The idea of Jupiter reaching this threshold is staggering, transforming from a colossal planet into a glowing, sustained powerhouse of nuclear fusion. This is where the concept of a second sun begins to take shape as an object emitting copious light, heat, and radiation, similar in nature to our own sun, but far smaller in scale. For Jupiter to ignite in this way, it would need to gather or retain an enormous amount of mass, possibly through some cosmic accident or a slow accretion of surrounding material. Once ignited, Jupiter would begin fusing hydrogen into helium, incrementally shining brighter and hotter, radiating energy across the solar system. Its atmospheric composition would change dramatically as new layers of fusion-generated heat influence its gaseous envelope. The visual impact alone would be almost surreal, a second, dimmer sun casting new shades and shadows over familiar landscapes. The presence of a second star in our solar neighborhood would produce an environment primed for dramatic planetary shifts. Light levels would double, intensifying the glow on planets, moons, asteroids, and comets. The climate trajectories of many worlds would warp, oceans boiling under the increased radiation, atmospheres shifting as they absorb this new source of warmth. Tidal forces on moons like Europa or Titan could intensify, possibly stimulating geological activity or melting subsurface ice layers, unlocking hidden reservoirs of water or even life. On Earth, the addition of another luminous body in the sky would redefine day and night cycles, creating a perpetual twilight or extended daylight that might drastically influence biological rhythms. This surreal celestial addition would inevitably force life itself to evolve under a vastly altered energetic landscape. Yet, weighing the scale and power of such a transformation leaves us pondering profound questions about the cosmos. How does a star's formation, so rooted in the fundamental laws of physics, drive the destiny of planets? Could a planet-sized object in our solar system ever reach such stellar heights without divine intervention? If Jupiter became a second sun, it would cast a new light on our understanding of stellar life cycles, planetary stability, and the delicate balance sustaining life on Earth. It beckons us to question whether this universe is a static tableau or an ever-shifting dance of matter and energy, an unending pursuit of the extraordinary in the vast void. And perhaps, amid all the possibilities, the most haunting question remains: what does it truly mean for a world to ignite in the darkness? Criteria for a planet to become a star. In the vast cosmic ballet, the transformation of a planet into a star hinges on a delicate interplay of mass, gravity, and nuclear potential. For a celestial body like Jupiter to step beyond its gaseous persona and ignite as a star, it must first amass enough material to trigger sustained nuclear fusion in its core. Currently, Jupiter holds about 0.1% of the Sun's mass, a figure far from the approximately 75 times that of Earth needed to reach the critical threshold, roughly 75-80 times Earth's mass. Once a planetary body exceeds this limit, gravitational compression intensifies, elevating core temperatures to millions of degrees. These temperatures suddenly become hot enough for hydrogen nuclei to overcome electrostatic repulsion and fuse, releasing immense quantities of energy. The process resembles the early stages of stellar formation, where a molecular cloud collapses under gravity, heating to incandescent levels. In this scenario, Jupiter's dense molecular hydrogen, compressed by increasing mass, would start to burn, transforming from a massive planet into a full-fledged star. The glowing, radiant body would produce heat and light comparable to a red dwarf star, shedding its gaseous exterior as nuclear fusion stabilizes its core. However, achieving this transition involves more than just raw mass. The density and composition of the object matter immensely. A planetary core composed mostly of hydrogen and helium, with minimal heavier elements, is more likely to ignite. The presence of elements heavier than helium, metals, acts as a coolant, inhibiting the core from reaching fusion temperatures. For Jupiter to become a star, it would need to accumulate not only enough mass, but also maintain specific conditions of chemical composition to sustain fusion long enough to ignite a star's characteristic luminosity. When these criteria are met, the galaxy would witness a dramatic transformation. Jupiter, once a swirling storm of gases, would flare into a celestial lighthouse, radiating light and heat across the solar system. Its immense glow would bathe inner planets in warmth, altering climates, atmospheric conditions, and potentially triggering evolutionary leaps for life elsewhere. It would become a new beacon in our night sky, shedding light not just on its own existence, but on the universe's endless capacity for wonder. As we ponder this, an unshakable question persists. At what point does a planet cease to be mere matter and become a shining star, an eternal flicker in the grand cosmic symphony? Jupiter's mass and its proximity to stellar thresholds. Jupiter's mass is so immense that it holds the record as the largest planet in our solar system, weighing in at approximately 1.9 x 10^27 kilograms. That's more than twice the combined mass of all the other planets bar the Sun. Yet, despite its staggering size, Jupiter does not come close to igniting nuclear fusion, the process that fuels stars. It remains a gas giant, a planetary behemoth composed mainly of hydrogen and helium, barely tipping the scales towards something that could be considered a star. But what if it had just a little more mass? What if Jupiter had crossed a critical threshold, inching closer to the stellar boundary? The line between a giant planet and a star is delicately defined by mass, specifically about 75 times the mass of Jupiter, or roughly 0.8 solar masses. Should Jupiter gain enough mass, either by absorbing more material from the surrounding cosmic environment or through some cataclysmic collision, it could approach this stellar threshold. The incremental increase in brightness, heat, and internal pressure would be transformative. In such a scenario, Jupiter might ignite nuclear fusion at its core, becoming a kind of red dwarf star, relatively small and cool compared to our Sun, but still a shining beacon in the dark expanse. The light emitted would be faint yet noticeable, casting a dim glow across the outer solar system, altering planetary orbits through gravitational shifts, and possibly influencing the asteroid belt's dynamics. Heat radiating from a nascent star-like object would melt icy bodies in the distant reaches of the solar system, spurring new geological processes and even planetary evolution in ways currently unimagined. The proximity of Jupiter to the stellar threshold is a tantalizing brink, just holding its breath on a cosmic scale. If that boundary were nudged, the implications for solar system stability are staggering. The energy released would surpass that of a large gas giant, creating a faint star that pours light and warmth into the outer reaches of the system. This isn't just a visual change. It would influence the tides, the climate, and perhaps even the potential habitability of moons orbiting other planets. In a whisper of cosmic possibility, Jupiter's transformation could turn our familiar celestial neighborhood into a broader, more luminous entity. Our understanding of planetary formation, stellar boundaries, and cosmic evolution would be forever altered. Standing on the edge of such a transformation, one cannot help but ponder the fundamental nature of existence. Is the universe merely a set of rules that allow planets and stars to emerge, evolve, and sometimes become something completely different? As Jupiter inches toward that stellar boundary, the question remains, is our cosmic reality so fixed, or is it fluid enough to allow giants to ignite, stars to dim, and worlds to become something else entirely? The vastness of the universe leaves us with more questions than answers, each crossing of a threshold whispering the possibility that everything we know could someday change in unimaginably spectacular ways. Nuclear fusion conditions and Jupiter's core potential. The prospect of Jupiter transforming into a second sun hinges on the immense pressures and temperatures deep within its core. Under natural conditions, Jupiter's core is believed to reach temperatures of around 20 K, vastly cooler compared to stars like our Sun, where core temperatures soar above 15 million K. For Jupiter to ignite nuclear fusion, specifically hydrogen fusion. It would need to sustain core temperatures and pressures comparable to those in stellar interiors. Fusion on a planetary scale isn't just about the present state, but involves the potential for core material to reach critical thresholds where atomic nuclei can overcome electrostatic repulsion and fuse. Achieving such conditions in Jupiter's core would require a staggering increase in temperature and density, far beyond natural planetary processes. The core would need to reach millions of degrees Kelvin, creating a state where nuclei are so energized that they collide with enough force to fuse. Importantly, the core must sustain these extreme conditions long enough for fusion to become self-sustaining, transitioning from occasional fusion events to a steady chain reaction. This would mean a fundamental reconstruction of Jupiter's interior, where gravity compresses the materials until they are packed at densities comparable to stars. The immense gravitational weight of Jupiter itself puts pressure on the core, but even this might still fall short unless an external force or internal process pushes the conditions further. If Jupiter somehow managed to cross that threshold, the consequences would be breathtaking. The planet's thick gaseous envelope, mainly hydrogen and helium, would begin to fuse, releasing massive quantities of energy in the form of heat and light. Instead of the gentle, cold glow Jupiter now emits, it would blaze with increasing luminosity, dwarfing many of our stars in brightness. The entire planet would glow with a luminous corona, casting stark illumination on the solar system and potentially altering planetary orbits and cosmic balances. Heat waves from fusion reactions would push through the layers, transforming Jupiter from a cold, gaseous giant into a blazing stellar object. The intense heat would vaporize much of its atmosphere, creating expanding plasma currents that ripple outward into space. On a deeper, more awe-inspiring level, this transformation invites primal questions about the nature of planetary existence and the boundaries of cosmic potential. If planetary cores can evolve into stars under certain conditions, what does that imply about the resilience and fluidity of celestial bodies? Would Jupiter become a new star in our celestial neighborhood, bathing the solar system in eternal, radiant light? Or would the process be unstable, flickering out before it reaches full stellar status? As we ponder these cosmic possibilities, the size and energy of Jupiter challenge our understanding of what defines a planet versus a star, leaving us with an existential wonder. Are we merely spectators of celestial dynamism, or participants in the universe's constant act of creation? Impact on the solar system's gravitational balance. If Jupiter suddenly transformed into a second sun, the gravitational fabric of the solar system would be fundamentally altered in ways both immediate and profound. Currently, Jupiter's gravity influences the orbits of countless celestial bodies, tugging on asteroids, comets, and even the outer planets. Its mass, more than twice that of all the other planets combined, acts as a cosmic anchor, shaping the architecture of our planetary neighborhood. But replacing that gentle, steady influence with a blazing star of immense heat and light would induce chaos on a scale rarely pondered. Massive and luminous, Jupiter's new status as a second sun would dramatically shift gravitational balances. Its increased mass and radiation would swarm the region beyond Mars, destabilizing the asteroid belt and triggering a cascade of orbital shifts. Planets in close proximity, like Mars and Earth, would feel the new gravitational tug, causing their orbits to gradually drift. The balance of the system, which was delicately maintained over billions of years, would fracture as planetary paths constantly readjusted, seeking a new equilibrium amid the turmoil. The orbital resonance points that kept asteroids and debris in check could become unstable, leading to increased asteroid and comet impacts on the inner planets, a spectacle of cosmic violence. In addition to the gravitational upheaval, the influx of heat and light from a second sun would reconfigure the climate zones on the planets. Earth, bathed in an increased and uneven stellar glow, could experience hotter, more extreme seasons, or even a breakdown of its climatic stability. The reduction or dislocation of gravitational forces might also influence Earth's axial tilt, climate stability, and even the length of days. These shifts could dismantle ecosystems and alter the habitability of our home, turning familiar celestial patterns into unpredictable storms of change. The cosmic symphony that once allowed for a stable orbit and comfortable climate would become a turbulent, unpredictable dance. Ultimately, the entire structure of the solar system would transform into a dynamic, tumultuous arena. The orbits of planets would no longer resemble harmonious circles or ellipses, but would evolve into complex paths dictated by the new gravitational landscape. Distant comets and Kuiper belt objects could be thrown inward or flung outward, creating brilliant displays of cosmic fireworks or catastrophic collisions. The long-term future of the solar system would be uncertain, perhaps a rearranged cluster of planets orbiting two suns in a chaotic ballet, or a system on the brink of disintegration altogether. It invites an existential question. What becomes of our cosmic home when its delicate balance is shattered by the fiery birth of a twin sun? The universe's grand design seems tantalizingly fragile, and in that fragility, perhaps, lies its most awe-inspiring mystery. Changes in orbital dynamics of nearby celestial bodies. If Jupiter somehow transformed into a second sun, the ripple effects on the solar system's celestial choreography would be staggering. Its newfound luminosity and heat output would effectively turn a gas giant into a blazing star, drastically changing gravitational balances as well. Already the largest planet, Jupiter's mass is about 1/1000 of the Sun's, but if it ignited into a star, the gravitational tug it exerts over nearby bodies would spike dramatically. The orbital paths of planets, moons, and smaller objects would shift, no longer shaped solely by the sun's dominant pull, but now tugged in unpredictable ways by a nearby luminous giant. Objects in the inner solar system would experience profound orbital disturbances. Mercury, Venus, Earth, and Mars, currently locked into relatively stable paths dictated by the sun's gravity, would now be caught in a tug-of-war. As Jupiter's newfound energy radiates outward, its gravity would grab and hold objects differently, potentially causing some terrestrial planets to drift inward or outward over millennia. The entire orbital architecture might become more eccentric, with planets' orbits elongating into teardrop shapes, nudged by the shifting gravitational fields. In some cases, smaller asteroids and comets could be pulled into more chaotic trajectories, increasing the likelihood of impacts or ejection out of the system. Meanwhile, the orbits of the gas giants further out, Saturn, Uranus, and Neptune, would also be destabilized. Jupiter's new luminous mass would alter the gravitational landscape in subtle but significant ways. Instead of a smooth orbital dance around the Sun, these planets might shift into more elongated orbits, or even experience gravitational resonances that accelerate their orbital evolution. Moons that orbit Jupiter itself, or orbit satellites of the outer planets, would undergo radical changes. Some could be ejected into independent trajectories, while others might spiral inward towards Jupiter, drawn by the immense heat and gravity of the transformed star-like planet. The asteroid belt, previously a relatively stable region between Mars and Jupiter, would become a chaotic zone of chaos, as the new gravitational and thermal environment interacts with countless small bodies. Some asteroids could get trapped in new resonances, becoming mini-systems orbiting Jupiter's surface, while others might be flung out into interstellar space. The influence extends outward. Trans-Neptunian objects and even the scattered disk bodies would feel the shift. Their orbits could elongate or precess wildly, leading to an increase in cometary activity in the inner system, fueling spectacular, sudden celestial displays. As colossal energy, heat, and light radiate from Jupiter, now a star, new zones of instability and chaos would ripple through the orbital fabric of the system. All these changes spark a haunting question. What becomes of a solar system when its gravitational center morphs into a blazing star? The delicate balance that sustains planetary stability shatters. Would life adapt or fade? Could other worlds survive the chaos? Or would entire regions become celestial graves? The universe, forever unpredictable, leaves us pondering. Is stability merely an illusion, or can chaos give birth to new cosmic order? Radiation and light emission from a new solar body. If Jupiter transformed into a second sun, the celestial spectacle would be nothing short of staggering. Its vast mass, now radiating immense energy, would begin to glow with a brightness rivaling or even surpassing that of our original sun, depending on how it evolved. The light emitted would spread across the solar system, creating a dual aurora of light and heat that redefines what we think of as day and night. The intensities of such radiation would reshape not only planetary atmospheres, but also the fundamental dynamics of our cosmic neighborhood. This new solar presence would release an incredible cascade of electromagnetic radiation spanning the entire spectrum, from visible light to gamma rays, altering the very fabric of planetary climates. This increase in radiation from a second sun would generate a profound uptick in heat energy across the solar system. Objects previously frozen or chilled would experience a dramatic rise in temperature, igniting volatile planetary atmospheres and potentially destabilizing entire ecosystems. On Earth, this could mean a new era of heightened greenhouse effect, different weather patterns, and perhaps even sustained intense auroras circling polar regions due to heightened magnetic interactions. Meanwhile, planets like Mars, which are on the edge of habitable zones, could suddenly become more amenable to life or face catastrophic environmental shifts, depending on their resilience. The radiation itself would be more than just light. It would include energetic particles streaming out, impacting cosmic rays and affecting the space weather that bathes our planet at a fundamental level. The spectral output from a Jupiter-turned sun would be broad and complex. Unlike the sun, which has evolved a stable, relatively low-energy output, a massive gas giant igniting to power fusion reactions would initially emit a chaotic mix of high-energy ultraviolet and 10th-ray radiation akin to active stellar flares. Over time, as the planet burned its fuel, it might stabilize into a red or orange-hued star, continuously radiating heat and light. The energy flux reaching the planets would intensify, altering their atmosphere's composition and chemistry. Astronomers would see a new, luminous beacon in the sky, perhaps a dazzling, ever-changing orb that bathes the entire system in a vibrant, ceaseless glow. The sheer energy output could significantly impact our understanding of stellar evolution and challenge existing models of planetary atmospheres. The eventual luminosity and radiation levels of this new solar body would determine whether life could adapt or be wiped out. The sheer force of the radiation could peel back layers of atmospheres and strip volatile compounds from planetary surfaces, creating a hostile environment for most existing ecosystems. Conversely, some planets might evolve under this radiant umbrella into new cradle zones for life. Meanwhile, the cosmic dance would be irreversibly altered, with the radiation impacting the magnetospheres, possibly intensifying auroras and creating new belts of energetic particles. The sun, the planets, and the space around them would be transformed into a radiant spectacle where light and heat coexist in a new, unpredictable harmony. At the end of the day, pondering such a universe leaves us with an existential question about the nature of cosmic transformation and survivability in a universe driven by celestial catalysts of unimaginable power. Would life find a way to adapt in the face of such dazzling upheaval? Or are we all just stardust floating through an infinite, ever-changing tapestry of radiant wonder and destructive potential? Effects on Earth's climate and habitability. If Jupiter somehow transformed into a second sun, the repercussions for Earth's climate would be nothing short of cosmic upheaval. The giant planet, now radiating immense heat and light, would flood our skies with a new, relentless blaze. The infrared and visible radiation from such an enormous celestial body would warm Earth's atmosphere far beyond current levels, potentially raising global temperatures well above thresholds that have preserved life for millions of years. The delicate balance that maintains habitability, where liquid water can persist, would become dangerously unstable. Regions that once thrived with life could turn into scorched wastelands, as the increased energy input destabilizes the climatic systems. The distribution of heat across Earth would undergo a fundamental shift. Earth's axis, combined with the gravitational pull from a twin sun, could lead to altered weather patterns and more extreme climate fluctuations. Enhanced solar radiation would intensify the greenhouse effect, trapping heat and disrupting the natural cycles of seasons. Some areas might experience relentless heat waves, with temperatures soaring to levels incompatible with current life forms, while others could shift into unpredictable, chaotic weather regimes. Ocean currents, which are driven by temperature gradients, could become erratic, redistributing heat in ways that would have cascading effects on marine ecosystems and land-based climates alike. Vegetation, which depends on stable, moderate temperatures and adequate sunlight, would suffer severe stress. Photosynthesis might become impossible in many regions due to overheating, leading to widespread plant die-offs and a collapse of the food chain. The increased luminosity could also cause a significant rise in ultraviolet radiation reaching the surface, further endangering life on Earth's surface and potentially damaging DNA. The biosphere, as we currently understand it, would struggle to adapt quickly enough to such a rapid and intense change in environmental conditions. Complex ecosystems would fragment or perish, giving way to much simpler, heat-tolerant life forms, if they survived at all. In this new, blazing epoch, Earth's habitability becomes an open question. Whether life can persist under the harsh glare and searing heat that a second sun would bring remains uncertain. Could niches be found in shadowed craters, deep ocean trenches, or underground caverns? Or would the planet shift into an irreversible spiral towards inhospitable extremes? The possibility raises profound questions about the resilience of life and the fragile balance that keeps our world hospitably alive in a universe filled with chaos and wonder. Alterations in the asteroid belt and Kuiper belt. If Jupiter suddenly shone brighter, radiating a new, deathless glow akin to a second sun, the entire structure of the asteroid and Kuiper belts would undergo staggering upheaval. These regions, once defined by their subtle wildness and icy remnants, would be thrust into chaos by the surge of heat and light. In the asteroid belt, which is nestled between Mars and Jupiter, the increased solar radiation would cause asteroid surfaces to undergo rapid sublimation. Metal-rich asteroids, which are remnants of planetary formation, might start to lose their volatile components, transforming into stony or metallic cores exposed to the relentless glare. Some smaller bodies, initially stable, could be destabilized by the altered gravitational influences and increased thermal stress, potentially spiraling inward or outwards in unpredictable trajectories. Moving outward, in the Kuiper belt, a vast, icy frontier beyond Neptune, the consequences would be even more profound. The icy bodies here, composed mostly of frozen methane, ammonia, and water, would begin to warm dramatically. Their delicate ices might start vaporizing, creating transient atmospheres around some objects, turning them into miniature comets glowing under the intensified illumination. This sudden heating burst would blur the lines between dormant, frozen relics of the solar system and active, comet-like bodies. Some of these objects, exposed to sustained heat, could disintegrate or develop new, volatile-driven activity, adding a fiery, cometary glow to a region that had long remained cold and silent. This transformation would fundamentally redefine the architecture of the outside solar system, as new material gets ejected, redistributed, or reclaimed from the void. Furthermore, the dynamics of the belt regions would shift, driven by the destabilizing forces of increased solar influence combined with Jupiter's new role as a near-sun energy source. The original gravitational balance that kept these small bodies in relatively stable zones would be disrupted. As smaller objects absorb more heat, their orbits might shift chaotically, some being nudged inward towards the sun, becoming new mini-comets or meteoroids, while others might be flung outward into the depths of the solar system or even beyond. These escaped fragments could become dangerous, fiery travelers crossing the inner planet's orbits with unpredictable paths. The belt regions, once relatively stable reservoirs of ancient material, would transform into turbulent, active zones of collision, evaporation, and reshaping, echoing the chaos often seen in young planetary systems. In this scenario, the very notion of the asteroid and Kuiper belts as fossilized remnants would vanish, replaced by a vibrant, dynamic, and increasingly volatile environment. As the belts evolve, they force a reconsideration of the solar system's future as icy debris and rocky fragments burn and melt in Jupiter's newfound warmth. The cosmic ballet of collision and accretion would stretch into new patterns, and with that, the possibility that Earth might experience a more frequent shower of meteoric debris, or that the outer solar system might shed new light and heat, questioning the fate of planetary stability itself. Would these transformations herald a new era of planetary reorganization, or would it be a final, chaos-driven curtain call, an alien spectacle where life's fragile existence must confront the relentless energies of a star reborn? Potential for new planetary formation processes. If Jupiter suddenly ignited into a radiant second sun, the cosmic dance of planetary formation would be utterly transformed. The sky would be ablaze with an intense, luminescent glow, casting vivid shades of gold and white across the solar system. Such a luminous shift would create a new gravitational and thermal environment, fundamentally altering how celestial bodies coalesce and evolve. The added heat and radiation could trigger fresh processes of planetary accretion, potentially giving rise to new worlds, a cosmic phoenix rising from the fabric of space. In this blazing environment, dust and gas particles orbiting the sun would experience drastically different forces. The increased radiation pressure and heat would accelerate the migration of small particles, sometimes sweeping them outward or causing them to spiral inward more rapidly. These dynamic motions could lead to the formation of new protoplanets in regions previously deemed stable. The delicate balance between gravity, radiation, and angular momentum would shift, paving the way for a cascade of novel planetary embryos forming in zones that once remained dormant. This phenomenon could resemble the chaotic chaos of early solar system days, but on an amplified scale driven by a second sun's relentless radiance. Thermally, the emergence of a second sun capable of rivaling or exceeding the sun's own output would redefine the chemical and physical processes within protoplanetary disks. Volatile compounds, ices like water, methane, and ammonia, would evaporate in vast quantities, eroding material that once contributed to the growth of icy bodies. Conversely, the intense heat could enable the differentiation of planetary cores at a faster pace, accelerating core formation and changing planetary compositions altogether. These newly forming planets might develop atmospheres thick with exotic gases, sculpted by extreme radiation, and possibly giving birth to environments vastly different from the ones familiar today. Such a scenario hints at a universe teeming with potential for planetary diversity. The heat and light would forge conditions where complicated chemical reactions could flourish rapidly, fostering the emergence of complex molecules and perhaps even prebiotic compounds in fleeting niches. Old planetary zones would vanish beneath shimmering heat waves, replaced by a turbulent landscape teeming with fresh planetary embryogenesis. Could our entire understanding of planetary evolution be rewritten by such a violent, yet creatively fertile event? The question lingers. In a cosmos where a second sun ignites, what new worlds would eventually take shape, and would they hold the promise of new life, or simply dissolve into the fiery chaos of creation? Long-term evolution of a Jupiter-turned star. If Jupiter somehow ignited into a star, the universe as we know it would begin to shift on a scale almost beyond imagining. Initially, the transformation would be astonishing. A colossal ball of gas, once a planetary giant, shedding light and heat across the solar system with a radiance that would eclipse everything but the sun itself. The emergence of a second star would send out streams of intense radiation, bathing the inner planets in a new, brighter glow. The formerly cold, distant giant would now burn brightly, asserting itself as a dominant force in the celestial neighborhood. For a time, the planet's composition would stabilize as nuclear fusion ignited its core, converting hydrogen into helium and releasing vast amounts of energy. The universe might see a new brightness, a second source of light that could alter the trajectories of comets, asteroids, and even nearby planets. Over thousands, perhaps millions of years, the evolution of this Jupiter star would develop an awe-inspiring complexity. The planet's gaseous layers, once cold and inert, would become increasingly hot and turbulent. As fusion sustains its existence, the planet's outer layers would glow with a fiery aura, illuminating the outer solar system with a diffuse, amber-colored radiance. This transformation could lead to the formation of stellar winds, powerful streams of charged particles that would blow outwards, sculpting space around it in cosmic patterns. The effect on moons such as Europa or Ganymede would be profound. Ice surfaces illuminated by secondary starlight would undergo radical changes, potentially melting or sublimating as heat transfer increases. Their atmospheres could thicken from outgassing caused by the intense heat, transforming icy worlds into more dynamic, possibly habitable environments or at least radically altered landscapes. The long-term evolution would ultimately depend on the mass and composition of this new star. If it sustains nuclear fusion steadily, it could serve as a second, albeit smaller, sun. Its luminosity would gradually increase or stabilize, illuminating its surroundings with persistent warmth. This continued energy output might influence the habitability prospects of orbiting bodies, perhaps extending the potential for life in some regions of the solar system. However, if the fusion process were unstable or waned over time, Jupiter's star might become a variable object, flickering between active and dormant states, casting fleeting glows across its domain. From a cosmic perspective, this scenario raises profound questions about the fleeting nature of stars themselves and whether celestial bodies are destined to eternal states of change, or if their very existence is a transient spectacle, infinitely volatile and eternally mesmerizing. Implications for humanity and space exploration. If Jupiter were to suddenly become a second sun, the entire fabric of our cosmic neighborhood would be irrevocably altered, and humanity's future in space would shift in profound ways. This colossal transformation would imbue our corner of the solar system with extraordinary brightness and heat. Jupiter, ordinarily a distant, cold giant, transforming into a luminous beacon. Its immense mass and new nuclear output could rival or even surpass that of our current sun, changing the balance of gravitational forces. For Earth and its neighboring planets, the consequences would be staggering. Longer days, increased warmth, and a potential shift in orbit or climate patterns, reshaping life as we know it. This new star's radiance would cast an unyielding golden glow across the solar system, perhaps blinding in its intensity, forcing humanity to reconsider the very nature of our environment. On a practical level, space exploration would experience a seismic upheaval. With a second sun illuminating the system, the need to rely solely on our primary solar power sources could diminish, giving rise to new opportunities for energy harnessing. Meanwhile, the altered gravitational dynamics could influence asteroid paths, perhaps drawing some into new orbits or pushing others into deeper cosmic isolation. Human missions to other planets would face unprecedented challenges and opportunities. For example, spacecraft designed for deep space travel might now be able to use the extra solar energy to accelerate propulsion systems, making interplanetary and even interstellar missions more feasible. Conversely, the increased solar radiation might necessitate fortified shields and new safety protocols for astronauts venturing beyond Earth's protective atmosphere. The human experience itself would evolve in tandem with these cosmic upheavals. Agricultural cycles, climate zones, and habitability conditions on Earth could all fluctuate due to the intensity and spectrum of the new solar radiation. Humanity might emerge with a new sense of cosmic kinship, racing to adapt, to harness, or even to understand this blazing giant that once was just a distant planet. Scientific organization and technological innovation would unfold at an unprecedented pace, driven by the necessity of survival and curiosity. Space agencies might pivot towards studying this new stellar body directly, seeking to decode the mechanisms that produced it and, more intriguingly, how to coexist with a star that was once only a planet. Yet among all the grandeur and potential, questions linger in the dark corners of the mind. What does it mean to have a second sun staring back at us? Would this redefinition of our starscape make life more resilient or expose vulnerabilities we have yet to comprehend? As Jupiter's transformation blazes across the night sky, it stirs a profound existential debate. How do we adapt? What do we preserve? And when do we decide to follow this new celestial light into uncharted territories? The universe's vast, mysterious dance continues, casting long shadows and brilliant bursts of illumination, reminding us that even the grandest cosmic changes are threads woven into the ultimate fabric of existence. Theoretical models and simulations. In the realm of astrophysics, imagining Jupiter transforming into a second sun sparks a cascade of complex simulations and models aimed at understanding the profound consequences. Advanced computer models utilize the principles of nuclear physics, thermodynamics, and gravity to simulate the internal processes that might occur if Jupiter's massive gas giant core ignited into sustained nuclear fusion. These models often incorporate variables such as the planet's composition, temperature gradients, and pressure profiles to predict whether the core could reach the critical mass and density necessary for fusion reactions. Comparable to the Sun's simulations suggest that, given Jupiter's current composition, reaching that threshold would require an immense influx of material or an extraordinary internal catalyst, both scenarios bordering on implausibility under existing understanding. The heat output from such a transformation would dominate the solar system's environment. Athero modeling indicates that Jupiter's new fusion core would emit a colossal amount of radiation, dramatically increasing local heat and luminosity. Depending on the model specifics, this juvenile sun might radiate as a red dwarf star, less bright than the sun, but still capable of significantly elevating temperatures in the inner planets. Researchers use detailed energy transfer calculations to estimate luminosity changes, which in turn impact the climate, atmospheric stability, and even the potential habitability of nearby worlds. These simulations highlight that the rise in radiant energy would likely wipe out existing ecosystems and reshape planetary atmospheres, forcing life to adapt or perish. Further simulation work explores the dynamic gravitational effects, integrating celestial mechanics with thermal evolution. The newly born star would exert unprecedented tidal forces on planets, moons, and asteroids. Computational models suggest that orbital paths could shift dramatically, potentially destabilizing the asteroid belt or triggering increased volcanic activity on terrestrial planets like Earth. These simulations also illustrate how the increased solar wind and radiation would strip away atmospheres and alter magnetic field interactions across the solar system. The grand scale of these models emphasizes the interconnectedness of planetary physics, showing that the formation of a second sun from Jupiter would ripple across the entire cosmic neighborhood. Ultimately, these models confront us with awe-inspiring possibilities and humbling uncertainties. They underscore how delicate and finely balanced our current cosmic architecture is, while hinting at the unimaginable energy and chaos that could come from such a transformation. Could our universe support two suns, or would it push the existing balance toward chaos? Would humanity adapt, or would this event mark the beginning of a new cosmic era, one filled with brilliance or darkness? These are questions that our simulations, no matter how advanced, only begin to touch upon. The true answers remain woven into the fabric of cosmic mystery. Feasibility and scientific perspectives. Jupiter, with its massive size and swirling cloud bands, holds the title of the largest planet in our solar system. Its immense volume and composition, primarily hydrogen and helium, make it a fascinating candidate for transformative cosmic scenarios. If Jupiter somehow ignited into a star, the consequences would stretch beyond mere planetary upheaval. They would herald a new era entirely, bathing the inner solar system in an unexpected glow. However, the scientific feasibility of such a transformation runs into formidable barriers rooted in our understanding of stellar and planetary physics. To ignite Jupiter as a star, it would need to reach the temperature and pressure thresholds necessary for nuclear fusion, primarily of hydrogen nuclei. That means increasing its core temperature to about 10 million Kelvin, a feat unprecedented in planetary science. Despite its colossal size, Jupiter's density and composition are insufficient for natural thermonuclear ignition, unlike stars that form from gravitational collapse, such as the Sun. The mass required for a celestial body to sustain hydrogen fusion is roughly 75–80 times that of Jupiter, making Jupiter's own mass a fraction of what's needed. In other words, without adding enormous amounts of matter, something well beyond any current or foreseeable technology, Jupiter cannot become a star on its own. Contemplating the feasibility also demands pondering the energy balance involved. Simply injecting energy into Jupiter's core would likely cause it to expand, but still fall short of initiating fusion. The planet's gaseous makeup absorbs and dissipates heat efficiently, preventing a runaway process. The only conceivable way, though wildly speculative, would be a colossal collision with another massive object, perhaps a rogue planet or an interstellar cloud, instantly delivering enough mass and energy. Even then, the outcome might resemble a violent upheaval rather than the steady ignition characteristic of stars. From this perspective, transforming Jupiter into a second star appears astronomically improbable with current understanding and technology. On a grander scale, if the impossible were achieved and Jupiter did become a luminous, heat-generating body, it would drastically alter the dynamics of our solar neighborhood. Its new brightness would cast warm, persistent light over the inner planets, potentially affecting climates and the stability of orbiting bodies. Temperatures on Mercury and Venus would shift, their surface conditions potentially influenced by the new stellar radiation. The very nature of the solar system would change, perhaps suddenly more hospitable to certain forms of life or paving the way for new evolutionary pathways. It prompts a profound reflection. How fragile and fleeting are the cosmic balances that keep our solar system in check? And what does it mean for us when we consider the possibility of such unthinkable transformations? As we imagine Jupiter transforming into a second sun, the universe seems to expand even further in our minds. Light spilling across the cosmos, heat pulsing through the fabric of space, planets reacting in an intricate dance of gravitational shifts. This hypothetical giant, now ignited, would cast a new glow across the solar system, altering climates and rewriting the fate of countless worlds. It's a reminder of the vast, awe-inspiring scale of cosmic forces and how delicate the balance truly is. When we peer into these possibilities, we feel a profound connection to the universe's grand design, tiny observers on a tiny blue planet, gazing upward in wonder. Who knows what the future holds or what unseen forces are quietly shaping our fate? Until we explore further, the universe remains an endless story of possibility. If this sparks your curiosity about the universe's mysteries, stay tuned. There's so much more to uncover. We'll keep delving into the wonders of space, unraveling the secrets that lie beyond what we see. Join us next time as we continue to explore the cosmos, because perhaps, in contemplating the unimaginable, we find the keys to understanding our place in it all.